Board. Welcome everyone to the Winds and Currents webinar today. Today we're fortunate to have Mara Freilich presenting, and to give a little background, Mara completed her PhD in 2021 in the MIT Woods Hole Joint Program. She's now a postdoc at Scripps, and in the summer she'll start an assistant professorship at Brown. She's going to talk today about some work she's been doing in conjunction with a variety of people at Scripps, looking at data from aircraft measurements collected with DOPVIS and organized by Luc Lena. So I'll let you take it away, Mara.
Great, thank you very much. Thank you all for attending. I'm looking forward to the discussion with you all. So to get started, as Sarah said, I'll be discussing observations at submesoscale from an instrument called DOPVIS. This is work I've been doing with Luc Lena, with Sarah, and with Matt Maslow. And so I think one of the things that one of the really important questions, or among the important questions that a potential Odyssey mission would help us to answer, is what are the fluxes of energy, heat, and carbon, right? So how are these quantities transported? And in particular, what are the dynamics that control fluxes of these quantities? And the answer will probably be variable depending on the ocean region. The observations that I will be showing are from the California current system, which is a relatively unenergetic region. We look at maps of global currents, like the one on the screen from ECHO. But it's also a very economically, socially important region with an important fishery, ecosystems that we depend on. It's also culturally important. And with these currents being important drivers of this ecosystem as a whole. And so that's a reason to focus on this region in particular. But I think some of the lessons we have about the fundamental dynamics may be applicable in other regions, even more energetic regions. And so I was fortunate enough to participate in the S-mode field campaign. And this is an image from a few weeks ago this is from MODIS, where we saw a really dramatic cross-shore gradient in chlorophyll here, which is one of the features that stands out as kind of persistent about the California current system, and that's on scales of hundreds of kilometers. But if you think about this in terms of the fishery's importance, right, this is transporting carbon from the coast out into hundreds of kilometers away from the shore, potentially sustaining productivity, exporting carbon. But the question is, how far, what are the dynamics that are transporting this carbon offshore? How far is it going to go, and where is it going in the vertical when it does that? And to answer those questions, we need to look not just at this kind of scales of hundreds of kilometers, but really what is happening at these fronts where we have really dramatic fronts of chlorophyll on one side and no chlorophyll on the other side. And understanding the dynamics there is what is particularly important, I think, for questions of how far is this transport going? What will be its ultimate fate? And so while I was on the S-mode campaign, we're sampling some of this, I was sampling some of this biophysical variability. But at the same time, Luc and others were flying in planes, sampling the velocity, and that's what I'll be focusing on, although I'll be focusing on data from the pilot campaign and previous campaigns. This is very recent. And so at those smaller scales, the dynamics are called submesoscale dynamics. And I'm defining submesoscale here dynamically, not just in terms of the spatial scale, and dynamically in terms of order 1 Rossby number, meaning that the relative vorticity is order Coriolis frequency, With these large velocity gradients, I actually think what is particularly important is not just the vorticity, but that the divergence also is order Coriolis frequency. And as a consequence of that, you can have large vertical velocity as well at the submesoscale. And so these large velocity gradients, large vertical velocity are important. It's also, submesoscale is really important for energy fluxes. So the question of how is energy cascaded from the largest spatial scales to the small spatial scales, and ultimately how are kinetic energy inputs to the ocean dissipated, is really one of the fundamental questions we have. And there's a geostrophic, if we think about this in a very schematic way, or forward cascade of energy to smaller scales that is a break kind of at the deformation radius, which is thinking about what is the role of mesoscale dynamics, where you can have a forward cascade of mesoscale dynamics, then participating in an inverse cascade of this sort of geostrophic turbulence. But there is some energy that continues into a forward cascade, is eventually dissipated, and there is playing a role in frontal dynamic, or there frontal dynamics play a key role. And this is really the submesoscale part of it. And so if we want to know how can energy be dissipated at the surface by turbulence, submesoscale dynamics are key, where some submesoscale dynamics are participating in an inverse cascade of energy from smaller scales to larger scales, while others are participating in a forward cascade of energy to dissipation scales. And really piecing that out will be crucial. And so here I'm going to ask, given this dynamical definition, what is the spatial structure of submesoscale dynamics? And so focus on continuity and change in kinetic energy from mesoscale to submesoscale. And in doing so, I'm going to show some observational evidence of the importance of nonlinearity at submesoscale and introduce observational tools to help quantify that. And then I will discuss and show observations that allow us to treat the implications of this for kinetic energy fluxes. And so the observations, as I've alluded to, that I'll be using are the submesoscale observations from the SIO mass instrument. And I'll be using observations from two campaigns. One is a frontal region sampled during S-mode in 2021. So this was during the S-mode pilot field campaign, not the most recent observations. We got off the ship just last week. And then an eddy, two counter-rotating eddies in the Southern California current system sampled during an ONR TFO campaign. And so this instrument that I'm using, the SIO mass, it flies on a twin otter, is flown on a twin otter plane, and it actually takes multiple co-occurring observations of upper ocean currents. Interested in a hyperspectral camera that allows us to look at the implications for biogeochemistry, but also a number of wave observations. And so this is, I think, a really exciting instrument. I'm fortunate to collaborate with Luke and others on the observations from it. And one of the observations that's come out of using the mass, I mean, this is work led by Bila Both, and I think I should probably presented this in this webinar, but just as a reminder, is that when we look at sea surface height, which is especially important for looking at currents from altimetry, submesoscale, the spectrum transitions from a red spectrum at the mesoscale to a blue spectrum dominated by waves at much smaller scales, with the submesoscale really being that transition area in these observations from mass. And so mass is, so using these observations of mass, we can now ask what sorts of transitions might we see in a power spectrum, not of sea surface height, but instead of kinetic energy, if we're able to get direct observations of ocean currents rather than using altimeters. And so the instrument I'm using to look at these direct observations of ocean currents from this plane is called DOPVIS. And so DOT-Viz is a forward-looking camera on the Twin Otter. So forward-looking meaning looking in the direction that the plane is flying. And it has a field of view that's up to 4 kilometers away from the plane. And so I'll show a video. Essentially, this is a video from DOT-Viz of the sea surface. And what we do to look at the ocean currents from this video, so this is georeferenced, just a square under the field of view of the plane, is to then take a wave number frequency transform of this video itself, so of the visual observations. And then in this wave number frequency space, the dispersion relationships of the surface gravity waves show up very clearly, but they are Doppler shifted. And so to look at the currents, we can actually invert this, and we can get upper ocean currents and actually upper ocean shear as well. But I'll be focusing here on the depth average currents. And the details of this methodology are in a number of papers, including one that Luke is leading in preparation as well. But this is a well-established methodology for estimating ocean currents. And so this particular instrument, the horizontal resolution, is 128 meters at the smallest end, up to 1 kilometer. The depth range over which it's estimating the currents depends on the wave conditions. And so here I'll just be using the depth average currents, and won't be treating any issues that have to do with this upper ocean vertical shear, although that is an exciting part of these observations as well. And so in terms of the first result, what is the kinetic energy spectrum? So we had some expectations that we might see a transition at submesoscale based on a transition from these two-dimensional turbulence to a three-dimensional turbulence. What we found is that the spectrum was fairly continuous from the mesoscale, so from scales of 100 kilometers all the way down to scales of just 1 kilometer. So here I'm using the 500 meter. So here I'm using velocities at 500 meters, spatial scale, spatial resolution. And I fit a guide of k to the -2 just to say that this kinetic energy spectrum seems to fit approximately k to the -2, could be k to the -5/3. They're very difficult to distinguish with this sort of observations. And this was true across both regions, both in this frontal region S mode, which is slightly more energetic, and then in the TFO observations, which were in those 2 counter-rotating eddies. And during TFO, we also had a ship-based observations that were, the ship was under the line of the aircraft. And so we can compare the observations from the top ADCP band on the ship to these aircraft observations in the upper ocean, and we see that those spectral slopes are also very consistent with each other. But the aircraft observations DOT-Viz allow us to extend to even smaller scales, so even farther into the submesoscale range. And I just want to point out, since this is the Odyssey webinar, the Odyssey resolution approximately will fall in the middle of this spectral range. And so in this analysis, I'll be looking at some dynamics that would be below the scale, some dynamics above the scale. Since this is a red spectrum, I think this is good news for Odyssey and being able to observe a substantial part of the kinetic energy. And that sort of transition around 10 kilometers, I want to point out, is also kind of the effective spatial, effective spatial resolution of a 2 kilometer model, and so which is state of the art for global simulations. And so when I plot the kinetic energy spectrum of this is actually a 2 kilometer regional run of MIT GCM that I showed on the title slide, we see a fall off at these scales just because of the effective grid resolution of a 2 kilometer model is much larger than that. And so these dynamics that we're able to study from the DOT-Viz instrument are at much smaller spatial scales than are currently available from both state-of-the-art global models and other observational tools. And so the first question was this expected? Is this consistent with previous results? And so Terry Tereskin compiled ADCP data from decades of cow coffee observations and in this particular region. And what we find is that what she found is that the kinetic energy spectrum was approximately k to the -2 at the mesoscale, which is consistent with these observations, again, that we have from the plane. And so this is fairly typical of this region. And so to get at the dynamics from a kinetic energy spectrum, one common method that's become common in recent years is to do a wave vortex decomposition. And so the idea here is that while kinetic energy, we're looking at velocity components, we can decompose those mathematical methods introduced by Oliver Buehler that allow us to decompose this into a stream function and a velocity potential. And that allows us to look at the spectrum of the rotational components associated with the stream function and the divergent components associated with the velocity potential. And in Terry's work with the ADCP, what she found is that the rotational components are dominant at larger scales, with the rotational and divergent components having approximately similar energy at the smallest spatial scales, which is to be expected, that we would have the dynamics be more in balance at large scales with less balance at small scales. But one of the issues is that wave motion associated with the divergent velocity, or is that a sort of divergent submesoscale? And when I began to ask that question, I realized that one of the assumptions of this wave vortex decomposition is that the velocity potential and stream function are uncorrelated with each other, that there's no interaction between the rotational and divergent components of the flow field, at least in a kind of mean statistical sense. And that really violates the assumption we have of how submesoscale dynamics work. So at submesoscale, we have order 1 Rossby number. We have this large velocity divergence, and not just large velocity divergence due to waves, but large velocity divergence that is forced by or associated with the rotational field, meaning the quasi-balanced submesoscale field. And the order 1 Rossby number means that the dynamics become nonlinear, and that also implies a correlation between a velocity potential and a stream function. And so while that assumption is problematic, one thing that falls out of the mathematics of this derivation actually is that this kind of spectral Helmholtz decomposition, one of the kind of mathematical objects it treats is the cross spectrum between the U and V velocity, here defined as along the track of observations and across the track of observations. And so that cross spectrum must be real if the velocity potential, so if you assume that the stream function and velocity potential are uncorrelated with each other in a mean sense, that implies that the cross spectrum between U and V is real. So another assumption, which is less problematic, but I guess equally, probably equally violated for many submesoscale dynamics, is that the velocity field is isotropic. And the velocity field being isotropic means that actually that this cross spectrum between U and V is really small, so that it is approximately 0. So you have very small coherence. And so in our observations, what I find in both sets of observations, first of all, that this coherence is not small. It becomes smaller actually at the smaller spatial scales in this eddy region. But even in the eddy region, these black lines are showing kind of statistical significance threshold for coherence, meaning that we are able to say there is significant coherence in these observations, and we can analyze this cross spectrum between the U and V velocity as an important statistical object. So in the eddy region, we find decreasing coherence at small scales. In this frontal region, what we find is not, we find that there is a minimum in coherence at a particular scale, but then the coherence begins to increase. And I think that makes a lot of sense if you maybe kind of do a Fourier transform in your head, or just think of, when you look at the observations of the front, a front is sending the energy to small scales so that you have a sort of coherence at small scales in particular patches because of the way that this front is oriented. And then if we look at the cross spectrum, here I've divided the cross spectrum itself, so cross spectrum between a long track and a cross track velocity, into the real part in the solid lines and the imaginary part in the dashed lines. And I should say in the eddy observations, the reason I have these thin and thick lines is that we took some observations, or the planes flew in some long transects, which are really nice for looking at the energy all the way out to the mesoscale, down to some mesoscale and some in the shorter transects. And so to combine both transects, I combine both transects in the solid line, so we have more data, more statistical significance, but also wanted to show what it looks like when you go all the way out to the mesoscale, even though that data is somewhat limited. And what we see is that, so I'm going back, what we see in this eddy region is that at scales below around 10 kilometers, the imaginary part becomes dominant. And so we're violating this assumption that the cross spectrum is real, with these important dynamical implications that this is showing us where the flow is nonlinear. And in this frontal region, we actually have a transition at scales of just a few kilometers between the cross spectrum being mostly real to the cross spectrum being mostly imaginary, saying that this is the scale at which we have a transition to nonlinearity. And so one way to look at that, we can combine the coherence and then the phase tells us, so we can take the real and imaginary, turn it into an angle, that gives us the phase. And so when the u and v velocities are 90 degrees out of phase, that tells us that we're in this nonlinear regime. When they're in phase 0, that tells us that we're in this regime where the rotational and divergent components are separable from each other, meaning that it could be, for example, superposition of waves on eddies rather than interactions between waves and eddies, or ageostrophic submesoscale frontal dynamics, for example. And we see, when we plot it that way, we see similar transition scales of around 10 kilometers in this eddy region and around 6 kilometers in the frontal region. And so that was in a statistical sense, but the question then is, what are the implications of this now for kinetic energy fluxes and for these sorts of frontal dynamics? So I'm going to look at these are observations from S mode on a different day, where the plane flew across a front, and it flew across at slightly higher altitude, and that allows us to get actually two-dimensional velocity. So I'm going to focus here, because of the aspect ratio of this, on just a smaller region that is a frontal region. In this frontal region, we have, from the infrared camera on board mass, sea surface temperature that shows really rich spatial structure and also shows a fairly large front on small spatial scale. So here we're looking at a 10-kilometer segment, and we're seeing about 0.6 degrees jump in the sea surface temperature. And I've plotted the velocities on that as well. And from these observations now, when we have two dimensions, we can begin to calculate these velocity gradients that we're so interested in at the submesoscale that will tell us about these sorts of kinetic energy fluxes and the sorts of frontal dynamics that are operating, asking what are the scales of these frontal dynamics. And so at this front, we have strong velocity convergence. And we also have a buoyancy frontogenesis at this front. And related to that, we have a forward flux of kinetic energy. And so the kinetic energy I calculated using the coarse graining method of Louis et al. And a positive, and so I'm looking here at the kinetic energy flux across 1 kilometer, which is the largest scale at which we're able to compute the kinetic energy flux from these observations. And so I'm looking, and so positive values are a forward flux. So from 1 kilometer to smaller scales, negative values are an inverse flux. So from scales of 1 kilometer to larger scales. And we see a largely positive flux of kinetic energy associated with the strong sea surface temperature flux. But there are also other features. And so I'm going to zoom in on just 2 features. First on the front. And just to emphasize that we have these really large values of kinetic energy flux that are large, but they're consistent with the results that are beginning to emerge about kinetic energy in terms of their magnitude, with the results that are beginning to emerge from high resolution models about the magnitude of kinetic energy flux at submesoscale. And so while we expect this forward cascade at fronts, I just want to point out there are a lot of other submesoscale features in these observations. And we also see these large values of forward cascade localized in these other sorts of submesoscale features. And looking at the IR temperature, so now this is a submesoscale feature that has a temperature jump of 0.1 degrees, which is noticeable, but much less dramatic than the front. And we can begin to see in this IR the signatures of Langmuir turbulence. And so we are at these scales and the features about 1 kilometer where we have this coexistence of boundary layer turbulence and submesoscale dynamics. And that has really important implications for how this forward kinetic energy flux may go eventually to dissipation. And so while I said this entire frontal region is a region of strong nonlinearity, when we look at it in this sense, we see that really these sorts of dynamical processes that have to do with these kinetic energy fluxes, convergence, frontogenesis, happening at even smaller spatial scales. So at scales of just 1 kilometer or even smaller. And just to highlight that again, this sort of intermittency of kinetic energy flux. So here showing PDF of the kinetic energy flux from the whole transect. And we see that actually both the positive and negative fluxes of kinetic energy have these skewed distributions. And so while the kinetic energy flux in this frontal region was overwhelming, was predominantly positive, we have large tails in both positive and negative flux. Yeah, and so I'm just going to wrap up to take a few minutes in connecting back to the motivation. So I motivated this understanding of the dynamics as being in this region that's particularly important for fisheries, where the primary productivity forms the base of the food web, and saying primary productivity is shaped by some mesoscale dynamics. And so while I was focusing on these dynamical quantities, frontogenesis and flux of kinetic energy, these submesoscale dynamics are also known to be important for transport of material as well, right? If we have convergence and flux of energy and buoyancy, we can have flux of material as well. This was shown really dramatically in these drifter observations, where each of these points is a drifter. In the Gulf of Mexico, where we see these drifters all accumulating. And this is the type of material transport that we might expect to see from these dynamics on scales of a few kilometers. And I don't have time to talk in detail about ecological impacts, but this is the topic of some of my other recent work. Where we showed, so what happens if you transport biological material down to those scales? So it's passive in the sense, so biological material is passive in the sense that it will not feed back in the dynamics. the way that transport of energy, flux of energy or buoyancy, or flux of momentum or buoyancy will, but it's reactive, meaning that the biological organisms are going to respond to the changes in their physical conditions in ways that mediate the impacts of physical processes. I did some observations in the Western Mediterranean Sea, where we have a chlorophyll filament, kind of resembling this, what we saw on the California coast. We have this high chlorophyll water at a front, and we sampled it at a very high resolution. And what we found is dramatic variation, even at scales of 1 kilometer, in the community composition in a front. And in a paper we've been review that co-led with Abigail Plummer, we showed that this divergence and accumulation of material at fronts can alter the outcomes of competition by phytoplankton, but that the rates of competition by phytoplankton have really important implications for kind of what will be the effects of this divergence. And so that's a small scales. If we think about this, right? So I showed those upwelling filaments, these distributions of chlorophyll like this. And one of the really key questions, I think, is how much is related to vertical transport and how much is related to lateral transport, and what are the interplay between those two. And that relates to these questions of what are the scales of fronts, what are the dynamics at fronts? Is this material being stirred by a largely 2D straining field, or is there participation by 3D dynamics? And that is a question that you treat partially in a 2022 paper in Geophysical Research Letters, where if we take a vertical velocity field with a mean nutrient profile, the key message, or one of the key messages, is that the rate of biological uptake of nutrients transported by a vertical velocity field affects the outcome of the distribution of those nutrients or chlorophyll that you can observe from a satellite image in 2D. And so if biology is relatively slow at taking up nutrients that are transported upwards by a vertical velocity field, then those nutrients can be stirred laterally, and we get this smooth lateral distribution. By contrast, if the biology is happening very quickly, the biological field will reflect the vertical velocity field, and vertical dynamics become much more important. And that doesn't mean that the flow has shifted from being a mostly 2D field with stirring to a mostly 3D field with vertical motion being particularly important, but instead that the interaction between biological and physical timescales is really key for shaping kind of what are the implications of these sorts of dynamics. And so to wrap up, what we found using these observations from DOPVIS is that the kinetic energy spectrum maintains a nearly continuous slope from mesoscales of hundreds of kilometers to 1 kilometer in this eastern boundary current region. And between scales of 1 and 10 kilometers, nonlinear interactions become dynamically important. And I introduced a tool that allows for diagnostics of these sorts of nonlinear dynamics. From these observations, we were able to show that both frontal dynamics and wave eddy interactions give rise to these sorts of nonlinear dynamics, meaning this correlation between stream function and velocity potential. In terms of kinetic energy flux, we find that intermittently large kinetic energy flux is localized at fronts. And finally, although I didn't go into the details of this, ecological interactions and biological processes both will eventually mediate the influence of these submesoscale dynamics on ecosystems.
Thank you, Mara. This is really great. Are there questions for Mara? And maybe I'll start while people are thinking of questions. I was really intrigued in thinking closely about your kinetic energy intermittency and wondering what that means for the overall kinetic energy budget. And I guess tied into that is what's the temporal intermittency of the kinetic energy transport?
Yeah. So I think one important way to quantify some mesoscales that, at least in my thinking, has emerged from thinking about this in terms of biology is that some mesoscale also has a particular temporal scale that's on time scales of a few days. And so in terms of temporal intermittency of a kinetic energy flux, if it's associated with those some mesoscales, spatial scales, meaning at 1 kilometer or so, we also expect a high degree of temporal intermittency, thinking about this in sort of a wave number frequency framework, where I think you would expect to see kind of temporal intermittency on timescales of less than a day. And that is a challenge for observations. If you're not able to take synoptic observations, it could be very challenging to accurately observe these submesoscale fluxes or kinetic energy fluxes.
Mm-hmm.
Hi, Mara. I have a question.
Yeah, go ahead.
Actually, I have two questions. One is that when you show the kinetic energy flux maps, I just got intrigued with some alternating tilted bands, and you have any comment on that? What do you think it might be, like these alternating positive bands for the kinetic energy flux and divergence?
Yeah. So I think there are probably a few answers. One could be noise. Another, though, is that so they also show up in the divergence, and they actually show up in the strain as well, which I didn't show here. And so I think that they could be related to sorts of fluctuations that may be physically meaningful within this front. And so part of the reason I decided to focus my snapshots on these two areas where we saw kind of correspondence between sea surface temperature and velocity is because I think they're a little bit more physically explainable. But I think I'm not used to looking at velocity observations of the ocean at these sorts of these sort of scales, right? And with this sort of aspect ratio. But if we go back to this overall frontal region, I think it's quite plausible, right? If you think about this in terms of an overall front, that there is a lot of variation within this frontal region. And the kind of key message is that while this dramatic, right, this largest sea surface temperature step is associated with most of the kinetic energy flux, there's also a lot of variation within this frontal region, which is some of what's emerging from ESMOD as being particularly important for these small scale dynamics.
I have another question, if I may make it. I'm sorry. So the other thing is that when you show the difference in community for the very small scales, and that kind of connects with the work by Shelja, Peter Frank's student. My question is that how much of that could be just generated by lateral transport of diverse communities that were brought together by the frontogenesis? Yeah.
So in this particular case, so I didn't go into the details of this study, right? So we're looking at this. I did track this high chlorophyll back using the geostrophic velocities. And I think one thing is, right, these are, what I found is that at least from tracking from the geostrophic velocities, it seems like these communities may have been coherent over timescales of like 10 days in their origin of the coastal region. It doesn't mean that there wasn't stirring involved in this generation of diversity. And so this study is actually mostly a modeling study rather than an observational study, where in the modeling study, we use Lagrangian tools to demonstrate that if you are able to follow communities in the Lagrangian sense, you can see a shift that's related to divergence that's mediated by the competition of the organism. But yeah, it's a good point. Yeah, and I mean, it's a fundamental point. When we're storing material together versus these dynamics having an active role in changing the outcomes of ecosystems or energy flux.
Thank you for a very nice presentation.
Yeah, thanks for your question. I see.
So Bia has her hand up.
Hi, Mara. That was awesome. Thank you.
Thanks. Bia.
I have it's more like an open-ended question / a comment, because it's something that I got myself thinking about it often. So one of your conclusions about the spectral slope of the kinetic energy, I wonder, like, as we approach, especially like with the with the last campaign in mind, where we had like a very coherent front, I wonder, like, how should we think about spectra, especially isotropic spectra, where like we're now starting to sample these like features as opposed to like a statistical view of the field.
Yeah. So one of the things about the spectral result here is, at least at the largest scales, and I'll go back. Yeah, requires a little bit of patience in my computer to go back quickly, but I'll tell you, and hopefully we'll get to the image. So Terry Truscott compiled the ADCP data from all the Kalkafi observations and showed this approximately k to the -2 or k to the -5/3 spectrum, mesoscale, so from 100 kilometers to around 10 kilometer scale. Even when sampling across just one feature or just two features, we found similar, right? So this is Terry's results with this k to the -2. We also found approximately k to the -2, even just looking at these features. And so I think in terms of your question, that first of all, one of the challenges of using spectra as a tool in oceanography is that the spectral slopes don't vary very much, which can make it hard to distinguish dynamics that are, say, k to the -5/3 and k to the -2, implying different dynamics. But the slopes, those two slopes, are very difficult to distinguish observationally with the level of confidence that we have. The other point I'll make, though, then, is that a k to the -2 spectrum is what it emerges from fronts, right? So if you capture a front in your region that you're observing, you do get a k to the -2 spectrum. And so that, I guess the point that I'm trying to make is that these particular features are what emerged kind of statistically. And by looking, right, so these are not isotropic spectra, these are just along a particular line. Yeah, and I think maybe the takeaway from this answer is that we need more statistical tools to actually disentangle the dynamics from our velocity observations.
Okay, thanks. Sorry, just since you are on this figure, did you have a chance to look at SSH spectra especially for the TFO data?
Only your results.
Okay. Okay.
Yeah.
Thank you. This was great, Mara. Thank you.
Yeah.
So in the chat, I think with reference to the kinetic energy plot, time evolution plot, Melanie has asked, could those repeating slanted features be internal waves?
I think related to the kinetic energy flux plot.
Yeah.
Yes, I think they could. Yeah. And I think internal waves, also potentially near inertial oscillations.
Thanks.
Yeah, that's a great point. Yeah. I see Tom.
So there's another question in the chat, and then we'll get to Tom, I think. Rick Danielson asks, if interactive processes involving, say, Langmuir circulation are at and below 1 kilometer scales, how should we think physically about nonlinearity at the resolved 1 to 10 kilometer scales? Are these the same, just resolved at our limits?
Another way,
Anyways.
I guess another way is to turn the question around. This is a great talk, by the way. And a lot of things I hadn't ever thought of before, like the decomposition into velocity potential and stream function. So it's an interesting new thing to think about it. But the tool you refer to is great. But another way of reversing my question is, would we still see this nonlinearity if there were no like Langmuir cells and there was no sort of really small scale, like not very resolvable scale processes going on?
Yeah, so one of the benefits of using observations here is that we're not, these observations should include any dynamics that are present, at least on the velocity. But we're not observing, and so I showed the IR temperature down, showing the signature of Langmuir. The velocity observations they were using were at 128 meters, and so they were not, right? So we while they include Langmuir, we're aliasing it at best, if it is having a meaningful imprint on the actual velocity. And so I think that's to say that this nonlinearity that I was showing, these 1 to 10 kilometer scales, is largely to do with semi-mesoscale dynamics, but those semi-mesoscale dynamics, and I think the point I was trying to make was that kind of at least we're at a point where we can begin to see both semi-mesoscale and Langmuir on the same plot, is that we know that those boundary turbulence mechanisms do alter the progression of semi-mesoscale instabilities, or are what would play a role, for example, in dissipation of kinetic energy from a forward cascade. And so, that's the point I was trying to make there. I think those are really the important questions.
There's a lot to think about.
There's a lot to think about here. Yeah. It was just exciting that we're able to observe it. Yeah.
So, and then Tom Farrar has his hand up.
Mara, so Melanie asked if those strike features in the kinetic energy flux could be internal waves. And you said maybe. How would they show up in this kinetic energy flux? Or what is that? Is it is there something in the way you diagnose that kinetic energy transfer that would make internal waves spuriously show an energy flux? Or if you think it's real, what's the dynamics of this cross-scale flux? I know that's a really hard question, but I guess I'd like to know what you think about it.
Yeah, sure. Yeah, and I should say that the analysis, this sort of kinetic energy flux analysis, is an ongoing active area of research for me, with these observations in particular. So this is something I'm actively thinking about and working on, and not a kind of complete closed story at this point. But one thing that's, I think, important, so this coarse graining method of computing kinetic energy flux, it makes it very clear mathematically that the kinetic energy flux is equivalent to velocity frontogenesis. At least you have to make some assumptions to get there, but so that helps at least me to understand. So if you have a wave that is participating in a sort of velocity frontogenesis, even if there's no net kinetic energy flux that would be associated with it, you could see a pattern of, right, when you look at it spatially and not averaged, as we tend to think, right? If you look at a kind of forward or reverse energy cascade, those are averaged over a certain space in a certain time. And as Sarah was pointing out, there may be a time intermittency issue there in a particular set of observations. So that's to say, I don't think it's spurious. It also doesn't mean that the waves would have a net imprint on a kinetic energy flux.
You mentioned the coarse graining technique, which I understand to be sort of like doing bandpass filtering. you know,
Yeah.
like a spectral technique, but with bandpass filtered
Yeah.
inputs. How did you do the filtering?
Yeah, I just got that question. It was a top hat filter.
Okay. I
And
wonder
so
if
symmetric and kind of 1 kilometer.
I wonder if there could be ringing or something that could introduce bands away
Yeah, I
from
think
a front.
I think that's a possibility. Yeah, and that was part of why I started this question, this discussion by saying it could be spurious, could be noise.
Are there other questions? If not, we will thank Mara again for a really wonderful talk.
Yeah, and thank you all for the great discussion as well.
I'm going to stop recording.